Hello, everybody. I'm Vance. This is Ross, and this is UKL Dynamic Linkage. So just a quick overview of what we are trying to do with this. Dynamically linked Unikernal Linux, full name, is a project that adds support for dynamically linked applications to the Red Hat project Unikernal Linux. UKL was this project that allowed the Linux kernel to. The Zoom keeps doing this weird.
Yeah, I don't know.
That allows the Linux kernel to statically link with a Linux application. This allows it to gain different kinds of unikernel optimizations for these Linux applications with very little change to the original code. Some more background on unikernels. They were introduced a while ago as these library OS things that compile and link with an application and its source code, creating a single bootable binary. This means that application that you've compiled has very low overhead. Pretty much everything that the operating system is doing is directly to serve this application. They were found to be really good for cloud environments because in those environments, you already have a hypervisor providing concurrency and isolation from other programs in the environment. You don't need the operating system there doing all of its work that it would normally be doing. Unfortunately, it has been found that these unikernels are difficult to program for. And so while there is a vibrant community of unikernels within research, they have yet to see much real application. So it's not this one. Yeah, that works.
Okay, yeah.
Yeah, so along comes Unikernal Linux. We thought, well, if people don't want to bring their applications to the unikernel, why not bring the unikernel to them? This is a small, about 500 lines of code patch to the Linux kernel that allows you to achieve those unikernel-like optimizations where you select a single UKL application, as we will call it, to link with the kernel statically. This creates a, by and large, fully functioning Linux kernel. You can still run regular user processes concurrently. You still preserve the entire Linux ecosystem, its ABI, and importantly, the entire Linux code base. There we go. So with this, we're allowed to achieve some optimizations that look a lot like unikernel optimizations. We have bypass where libc will typically make system calls. When we're in the unikernel, we don't need to make system calls. So instead, it can directly call these ksys functions that bypasses some of the bookkeeping that the kernel will do when you typically make a system call. They're shared stack. Since you're now sharing an address space with the kernel, you don't need to switch stacks every time you make a system call. That can avoid some overhead as well. If you want to get deep into the kernel and really make some significant optimizations, you can do this thing that we call deep shortcutting, where you call some function down the line after some of the kernel like multiplexing and polymorphism. For example, in this read flame chart, what we're reading is a TCP socket, and typically when you would make a system call, the kernel would look at the syscall number that you passed it, okay, we're doing read, then it would say, okay, we're reading something from the virtual file system, then it would do some bookkeeping, then it would go, okay, it's this kind of socket, it's that kind of socket, and then finally you get your read. With the unikernel, you can avoid all that. You can just call TCP read yourself and get some nice performance improvements.
Made the slide. So the problem with a static unikernel is that you have to perform extensive code surgery for every single application that you port. It takes a long time, it's pretty hard, and what you're doing is compiling your application with the kernel into a single binary image. And so it's very rigid and tightly coupled. If you just make one change to your app, you have to recompile the whole thing. So it's very rigid and hard to work with. And you have to do extensive edits to compilation scripts such as make files and whatnot. Oh, I made this one?
Yeah, I can do this.
Yeah.
So why we want to support dynamic linkage, kind of the converse of the problem with static linkage. Applications use dynamic linkage in a lot of very intricate ways. Most of them will use it just for standard shared libraries. Redis, one of our favorite target applications, there was quite a bit of work that needed to be done to include the libraries that it was expected. There are other applications, for example, literally anything that's written in Python that will use very deeply the runtime linker. It'll open up libraries every time you import a module, and that kind of thing we just can't do with static linkage without effort that would, without significant effort that would kind of defeat the purpose of UKL. Like Ross said, makes it possible to ship a single kernel binary. This is kind of how companies like to develop their operating systems. Instead of like having one for every single application you write, just have something, you send it to people, they run their applications. Support for exec, importantly. If you have multiple applications that you want to run on a single kernel in a single instance as a UKL application, you could do that with dynamic linkage because now you can just load in a new application. Something else that we discovered as we were developing this, using dynamic linkage significantly reduces the patch sizes of both glibc and Linux. So a little bit of background, I was talking about dynamic linkage. That uses this file format ELF, which is the format of all executables on Linux systems. ELF files come in three forms. They can be shared objects, they can be executables, they can be object files. I'm going to focus on the shared objects. Those have basically all the features that an ELF file can have. They are used when we have some standard code that we want to reuse between different applications. So for example, libc, basically every application uses it. Libc is, I think, about 10 megabytes the last time I checked. We don't want to have that packaged in with every single binary. We don't want every single memory address space on our system having its own copy of libc. So we use shared objects that have these shared memory mappings. They have position independent code. These are things that we do not see in kernel code. It's just this one single binary that exists in this one spot in the address space and it never moves. So there is going to be some work that we're going to have to do to make the kernel appear to the application and to the dynamic linker as a shared object. There's another thing, with a lot of that shortcutting we talked about, we really care about these functions, these symbols that we need to be able to call. Shared libraries use this thing called the PLT, the procedure linkage table. That is a small code stub. You can see it right here. It'll do some jumps. If it doesn't find what it's looking for, if the function has not already been loaded, it'll run through the dynamic linker. And this has some large overhead, but after that, the function address will be loaded into memory, and it's just 2 extra instructions before you're at your function. Importantly, in order to do these PLT lookups, in order to resolve these symbols in the PLT, the dynamic linker needs to do some work. The dynamic linker is just another user application that runs in the same address space as the application that you're trying to run. So if we're running the UKL's applications dynamic linker, the dynamic linker itself will also need to run in supervisor mode. And so if we're using the dynamic linker to look at these kernel symbols, but the dynamic linker itself needs some kernel symbols, we need some way to resolve that. And we'll talk a bit about how that's going to happen. So a quick overview of the actual roadmap to implementation. First of all, we need to patch our build systems for glibc, Linux, and the target application to use dynamic linkage. We need to make sure that the kernel is actually loading the UKL application now, because it's not just going to be in memory because the bootloader put it there, because it's not a part of the Linux executable anymore. We need to change the way that glibc uses kernel symbols to redirect it through the PLT. And finally, we need to export the kernel symbols into a shared object so that the dynamic linker is able to access them. So before I mentioned that we need to figure out a way to get the runtime linker to access kernel symbols. Turns out, fortunately, the only kernel symbol that it needs is the entry point, that is the place that the kernel will jump to when you make a system call, because it itself needs to make system calls. And the way that we ended up doing this was we will pass entry syscall 64 in a register to the dynamic linker because it is the first thing to run, and the dynamic linker will just save that in a function pointer that it can then reference using this little syscall stub right here. So within Linux, we got to do a lot of scrapping of some old things that we needed to use dynamic linkage. We could get rid of all of the edits to the linker script that required the UKL application to be loaded in. We also, because now the UKL application is just another file in the file system, we need a way of identifying which of those files in the file system correspond to the UKL executable. We decided to use that. We created this directory data that would host all of the UKL data. If an executable is found in there, we consider it the UKL application. Then after that, when we're actually loading the UKL application into memory, there were a bunch of things that we would have had to skip if we were doing this statically, if the UKL application was already in memory and didn't have to be loaded from the file system. We don't have to make those exceptions anymore, so that was more code that we were able to remove. And then finally, actually passing that entry syscall 64 down to the dynamic linker. For this, I use the register R15. I don't know if that's like a violation to the ABI or the compiler's assumptions, because maybe it expects everything to be 0 when the program starts, but I haven't run into any issues yet, so I'm just going to assume it's fine. Within glibc, again, we need to receive that entry syscall 64 from the kernel and put it into our special runtime linker buffer so that it can make syscalls. I then, just to be safe, XOR out that R15. Then within the rest of glibc, we need to go through and replace all the places that it makes a syscall, because most of the time when your application is making a syscall, there is not actually a syscall opcode in the program's executable. It's going through glibc, and glibc is the one making the syscall. That makes things really easy for us because that means that most of the time we can just rely on the fact that glibc no longer contains any syscalls, and so just go through, replace it with this syscall method, which is actually a preprocessor macro that either makes that PLT call to entry syscall 64, or it goes through that function pointer if it's in the dynamic linker. Then within the build system, another place where things become a lot easier, these are the git diffs edit between the static linkage and the dynamic linkage. You can see there's a lot of red here and not a lot of green here. That's because for the most part, we are able to just take the executable out from the build system, whether it's like Redis or memcached, put it into our file system. The one edit that we do need to make is we need to run this patchel, because once again, we are trying to have a fully fledged Linux system. We are going to have a regular dynamic linker. We are going to have a regular glibc that are going to work with normal user applications that are going to contain syscalls. We don't want that. We want you using our dynamic linker. We want you using our shared libraries. And so we use this set interpreter, set rpath, to tell the Linux kernel and to tell the dynamic linker to instead look in our data directory.
So just to reiterate, with static libraries like archive libraries, you have to embed the code into the executable at compilation time. And so for unikernels, this means you have that single binary image. Whereas with dynamic shared objects, you do symbol resolution at runtime. And so you have a single copy of this code, and then the dynamic linker loads the code into memory and the programs call it. And so this decouples the unikernel from the app. And so you don't need to recompile the kernel after you change your application. So I was in charge of building the shared object. Now, the great thing about this is that the only change we made to the kernel was exporting the klsims lookup name in the config. This used to be exported by default, but I guess it's not anymore, so we exported it. It just gets you the symbol definition, the address of a kernel symbol. And so this whole thing, like we have after, or like during initialization, during boot, we insmod a kernel module, and then we perform an ioctl with symbol names And then with this ioctl, the kernel module uses that klsims lookup name, gets the addresses of all of these functions, and then passes them back in an array. And then we use that with LD to build the libuklsims, the shared object. And then we link our applications with this whenever we compile them. And so they have all those kernel symbols that they need, including like some of the bypass ones that Vance was talking about with that like flame chart where you can go further up and save some time. And what's great about this is that this was probably like a few hundred lines of code, but it's all in user mode. Like it's not changes to the kernel. So we're hoping that like, you know, one of the main motivations for dynamic UKL is to get it upstreamed, because with static UKL, it's like you have to do all this recompilation. It's very complex. You have all these, you know, changes to the kernel, but with this, it's very minimal and very easy. So that's one of the main motivations. Just to reiterate the benefits of our approach, so the kernel module is inserted to create a shared object at each boot. So even if you have ASLR, address space, layout, randomization, then it still works because, you know, it gets these addresses of symbols at runtime. So, and then, you know, you can recompile your app anytime. There's minimal changes to the kernel source code, and the code is compatible and portable. So like, you don't really have to make changes to the source code. Like you have to like call the patch L for like, do these little things on the outside, but the actual source code, you don't need to make like, you know, 100-line changes to your make file. So it simplifies the adoption and ease of use. Rigorous testing. So I guess I have like one data point there. I'm gonna get some more data points, but I was running this earlier today, and the main thing is that it runs. This is with Velky. So it's like a key storage server thing. And I was showing Eric the numbers and he said it looked good. I don't have a baseline to compare against, but, you know, I'll take his word for it. But yeah, the main thing is that we have this working and it's very easy to use. So hopefully, you know, this number, as Eric said, is pretty good, and compared to a static baseline, it performs well.
So if you compare this number already with the static baseline doing the same operation,
It lined up, so we only have one run of this, so it's not statistical yet, but it lined up with the same latencies and throughputs we were seeing with the static.
okay.
It wasn't exactly the same, but it's also a different code base, so.
So it's parentheses rigorous testing.
Yes.
Yeah,
Yes.
I forgot to add that.
Some restrictions apply, whatever, you know, your mileage may vary, etc.
Anyways, results, it works. UKL can now run dynamically linked applications. We can, like I said before, with now support for the execsys call, we can run any number of UKL applications within the same instance of UKL. We got those reduced patch sizes for Linux. It was around 40%. Most of that was just taking out the linker script. There were a couple of other things we were able to remove. For glibc, the results were much more significant. It turns out that glibc really does not play nice with static linkage. And so by finally just not having to do all those build system workarounds, we were able to reduce it to just 250 lines of code. Something that I think would be reasonable to actually make a case about upstreaming. You can see like the 5,000 or either 1,700 lines of code, depending on how you look at it for the static patch. That was because there were a lot of file copies that had to happen. And if you only count the lines that were changed within the files that were copies, it's 1,700 versus 5,000 for like the full patch. And most importantly, it conserves all of the performance gains that we saw with the original UKL.
Your mileage may vary.
Mileage, yeah, sure. So our favorite application, Redis, you can see about a 10% throughput improvement on the Redis benchmark. That was about what we saw with the original UKL paper. Just for funsies, I also ran the Python HTTP server and saw about a 5% improvement in throughput. You know, a 5% improvement in latency, which, you know, is kind of modest, but the important thing, I think, is that one, we were able to do this with Python, run Python in supervisor mode and access kernel symbols, and two, do it with zero modification to application source code. For people more familiar with this project, they might think that that's a little bit of an exaggeration because to initialize this UKL bypass mode thing that I'm talking about, you need to call two kernel symbols that we inserted. That is no longer the case, again, because you can run other applications as a UKL application. You can use a separate application to do your kernel initialization and then jump into your unmodified target application and see these performance improvements. A couple of future directions for this project. One, ironing out some bugs. When we were running our Redis benchmark, we saw some kernel splats complaining about the RCU. We didn't see any change in behavior, so it could just be that the kernel's getting nervous that we're messing with things we're not supposed to mess with. But we'd like to resolve that before we say definitively this is complete. Replicate some of the other experiments. Ali, in his original paper, was able to do some of that deep shortcutting with Redis and see like 25% performance improvements. So replicating that, making sure that that still works in our new patch. And then finally, a library of those deep shortcuts. The kernel is a very big place, and just asking people, hey, just pick out functions you want to call, can be a pretty daunting thing. So kind of like a map of like, hey, your application wants to do this. You can call these functions and you'll see these performance improvements. I think would be pretty cool.
We also have like a section for lessons learned. Because last time, I think when I did like a Red Hat presentation, they asked about like, what did you learn? So,
Learn by doing.
one of the things I learned was like, I mean, this seems intuitive, but you gotta have like scripts for repeated tasks with comments. That saved us a lot of time because initially we were just like, okay, you learn how to do this, you learn how to like, run these tests, but why not use a script? Another one, ask how and why. So I spent a little bit of time on the glibc port and I was like exploring like dissecting the library, trying to get it to compile and like, changing things when actually I ended up just like writing a script that helped out with what Vance was doing where it just replaces the syscalls with that stub of code. So made the problem a lot harder by not asking enough questions. Okay, documentation in a readme.md. So we want people to be able to port their applications to dynamic UKL very easily. And so having this documentation, we do have documentation, but then just like more documentation is great. And then also having one branch. So there was lots of different branches that we had. And it took a lot of time to coordinate like the submodules and be like, okay, is this the right combination? And ultimately, we really just have like, I would say like 2 to 4 like unique builds of this where it's like you have static, dynamic, and maybe like static with some other stuff.
Some other lessons, persistence and open mind are the only prerequisites you need. When I went into this, I don't think I even really comprehended the problem that Arad and Eric were describing to me. I am pretty sure at just about every point along this project, I doubted if it would ever get done. But kept at it, spent a lot of time reading ABI, spent a lot of time reading the one textbook on linkers, and it got done. And I left with a much deeper understanding of the C language, linkers, which are a bit of a lost art to system students of the day, and ELP formats. Number 2, the rubber duck debugging method is a powerful technique. Somewhere along the way, I realized when I was struggling with like how to manage the different like things in glibc that the libc maintainers actually had a mailing list that you could ask them questions to. And I'm like, oh my gosh, this is great. I don't have to like struggle with this on my own anymore. But I was also like, oh my gosh, these are the glibc maintainers. I gotta make sure I ask some really good questions. And so I would kind of be working on a problem and I'm like, oh, I wonder if they can help me with this. I would spend so much time like crafting these questions, thinking about like what my assumptions were, how the behavior of the system was violating my assumption, that most of the time I would just, in that process, realize the ways in which there were gaps in my knowledge or how my assumptions were wrong, and the problem would resolve itself on its own. Lastly, systems research is just cool. This has been, without a doubt, the coolest thing I have done at BU. And I'm just incredibly grateful to have had this opportunity to work on this project. Thank you. Special shout out to Eric Munson, Aisha, Aran, and the glibc maintainers, of course, for all their support.
I think it's super cool. I mean, I'll just start. First of all, glad that you got it working. Even if RCU is not super happy with you. That's yeah, I'm from RCU all the time. The other thing I want to ask you, I understand that you can now have these applications that are essentially dynamically loaded. But what happens to library that these applications depend on? Can they go and load dynamic libraries from the standard, the library path from the system, or do you also have to put those shared objects, compile them in a special way, and throw them into the /data folder?
Yeah, they can load. You can load dynamic libraries from wherever.
From wherever.
Yeah, I'm not sure if like the fact that we set our path to /data means that the dynamic linker will only ever look for shared libraries in there. But as far as like what would work with the application, as long as it's not issuing a syscall directly, the UKL application can use it.
Oh, as long as it's not issue, which typically they go through glibc anyway to do that, right? So as
Yeah.
long as you have a patch glibc. And the other thing is like, okay, but now you have a situation where you have a shared library has been loaded, so it's in memory. And typically in that case, other user space applications, normal user space, would like to use the same library. So for example, they load the same library. Do they share physical pages now? And just-
For the dynamic libraries, yes, they do.
Yes.
It works, the page cache is page cache.
Okay. But that now, of course, introduces a security problem, because then if you have a user space application, which is non-privileged now, could potentially mount a privileged expression attack up to kernel level, even if you don't have pseudo privileges, right?
So your privilege is attached to your task, not to the libraries you're using.
True, but if you are mapping the same exact library, typically the way this side channel attack work is just because they rely on the fact that they can map the same exact physical page and therefore reconstruct data that was that was mapped to the other user of that library.
Sure.
So like you can use regular user libraries. You don't have to. Like if there's one application that gets like all of its own shared libraries itself, it can be the Unikernal. And just by placing everything in this data directory, because they don't have the same path, the kernel won't consider them the same library, and it won't use the shared memory mapping, if that's your concern.
I might also fall back on the, because the security people aren't here, that this is Unikernel research and security went out the door when you came in to talk about it.
But careful, right? This is
Yeah.
true. If you're assuming that you can do damages people with root access, but here, if you start extending the damage to non-root applications too, then
Well, there's no reason we can't hide UKL behind SUID 0 as well. You have to be root to be able to start this, et cetera.
oh yeah, for sure. So, no, but again, yes, but make sure you don't have like a non-privileged application that can cross that Rubicon, right? This is super cool. Yeah, that's nice. Sorry, I don't want to monopolize the discussion. So,
Yeah, we're at time, so maybe one more question.
okay.
So-
Go ahead.
So, I really like the project. I have just one question. When you do shortcutting and bypassing, right? We are not doing a lot of the kernel bookkeeping because there is the hypervisors that will do that for us and figure out if we can access that resource or what is the result of that system, right? So in a way, we can resolve the security issue there by adapting hypervisors to the UKL and making sure whoever mounts a shared library, they need to go to additional chunks if you want. Because I'm imagining that a UKL application is containerized as one single VM in the hypervisor. So you still have a somewhat degree of security because then the other advisor will check if what your PM is doing is right or not. Is that more or less the case?
So, I mean, there's no reason you can't deploy it that way, but we don't assume that you will,
Okay.
right? And I think the point that Renata was making is that we support a full user space. You wanna start SSHD with it along so you can watch it, great, go ahead and do that. You wanna do other things that do like key rotation or logging for you, you can do that too. And if any one of those uses a shared library that is also used by the UKL application, they become a vector for exporting information from the UKL application.
Okay, so maybe we need to wrap up, but just one last question. So are you telling me that I can throw the bash interpreter in the data folder and have a kernel level bash?
You can in fact do that, yes.
That's useful.
Super duper user mode, we call it.
Super duper user mode. Interesting. I want to see that in action at some point. Yeah. All right. All right, please thank the speakers again.